You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So if you've ever taken a basic geometry class, say in high school or even middle school or elementary school, you may have learned these indisputable facts. The angles of a triangle add up to 180 degrees, for example. Or the circumference of a circle is equal to 2 times pi times the radius of the circle. Or parallel lines never meet. And all these facts are true in what we call Euclidean space, or flat space. Not just two-dimensional, like a piece of paper, but also three-dimensional flat space, how we typically think of space in our universe. But it turns out that Euclidean geometry is only a special case of what the geometry in our universe actually is. The universe can, in fact, break these very basic rules. And in this episode, we'll talk about how this new understanding of geometry lets us see the universe in a whole new way, and how Einstein used it to devise his theory of gravity. So let's talk some more about Euclidean geometry so that you can get a sense for how ingrained these ideas are in our ideas about space. They almost feel obvious to us.
So Euclidean geometry is named after this guy, Euclid of Alexandria. He was a 3rd century BCE mathematician and philosopher. He wrote this book called Elements. And this is like the home run of book writing, because not only was it like a bestseller, but it remained a bestseller for 2,000 years plus. It was the book. If you had one book on geometry on your shelf, if you were a serious mathematician, it was probably Euclid's Elements until, I don't know, like the late 19th century. This was everything you needed to know about geometry. Euclid wrote down, 2,300 years ago. And it looks a lot like the kind of geometry, you and I probably learned about in high school. Euclidean geometry is an axiomatic system. What I mean by that is Euclid starts with a series of things he just asserts to be true. He just says, these are true, and from these things, I'm going to derive other things that are true. I'm going to prove other things. But those things you prove are only true if those axioms are true. So everything relies on the axioms. These axioms are things like, if you take any 2 points, you can connect them by a straight line. Or all right angles are equal to other right angles. These sound pretty uncontroversial. The 5th one, the most interesting one, is that for any straight line, there's exactly one straight line that's parallel to it that passes through any given point in space. So for that 2,000-year plus history, everyone seemed to agree with Euclid that this had to be the way the world was. Mathematicians and philosophers just looked at these axioms and said, well, how could they not be true? They're just obviously true. They're intuitively true. The great philosopher Immanuel Kant went as far to say that Euclidean geometry was the only kind of geometry that, I don't know if he said that it could exist, but at least the only one that the human mind was set up to conceptualize. And, that's a pretty bold statement. And of course, it wasn't just mathematicians, but physicists too. Isaac Newton and the other physicists in the classical era all built their systems upon Euclidean geometry. As far as I'm aware, nobody in that era was thinking about how to do physics in any other system of geometry than the one envisioned by Euclid.
So you could also just think of Euclidean space as being flat space. For example, a flat piece of paper is an example of a two-dimensional Euclidean space. You can draw 2 perpendicular lines, say the x and the y directions, if you're used to thinking about that. But if you think about the surface of a sphere, for example, that's a two-dimensional curved space, and so it won't follow the same rules of geometry that we mentioned before. For example, if you draw a triangle on the surface of a sphere, the angles of the triangle will add up to more than 180 degrees.
Like, let's say I take the surface of a sphere, and I'm going to draw a triangle. I have to pick 3 places on that sphere to make my triangle. So I pick 2 places on the equator, and then I pick a 3rd location on the North Pole. I draw my three straight lines. The ones on the equator, those two vertices are 90 degrees each. That's because they're perpendicular. There's lines of latitude and longitude. And then the one at the North Pole, well, it's more than zero. So I add up those three angles and I get more than 180 degrees. That's because the surface of a sphere is a positively curved space. It's non-Euclidean. Now, it's really hard to picture that in 3 dimensions. But in a 3-dimensional non-Euclidean space, if I take 3 points in space and I draw straight lines, those lines curve. So it's kind of a counterintuitive thing, but what it means to be a straight line is a different thing in a non-Euclidean space than you might currently be imagining.
So like Dan said, this kind of non-Euclidean geometry isn't too hard to think about in 2 dimensions if you take examples like latitude and longitude lines on the Earth, and these kinds of examples have been studied for a long time. But it's when we start to think about non-Euclidean space in more than 2 dimensions where things get more abstract and confusing.
So certainly like cartographers and things had a lot of reason to figure out how to do geometry on the surface of a sphere. Like that's definitely something that people were doing. But I don't think it was until the 19th century that people started to try to do this in 3 dimensions. So here I have in mind, like there were a bunch of mathematicians who contributed to this, but like one of the most famous is Bernhard Riemann. He was a German mathematician in this time. And then I'll just mention like there was Janus Bolyai and Nikolai Lobachevsky, Hungarian and Russian mathematicians. And these guys started to go back to Euclid's axioms and saying, well, can we jettison any of these? Do we have to adopt any of these? And my understanding is that they proved that the first 4 of Euclid's 5 axioms you really do need just for like internal self-consistency. If you threw any of them out, you just wouldn't have a system that makes any sense. But the 5th one, you can jettison the 5th one, the one about parallel lines, and still have self-consistent geometries.
So Euclid's 5th postulate said that if you have any straight line and you choose any point not on that line, you could draw exactly one new line that passes through that point and is parallel to the first line. But in non-Euclidean geometries, this is no longer true. For a geometry that is spherical or elliptic, parallel lines curve towards each other and meet, just like the lines of longitude meeting at the poles. So you can't really draw any lines which satisfy the postulate. And for hyperbolic space, what we call a geometry with negative curvature, you can actually draw infinitely many lines that satisfy the 5th postulate. But what does this have to do with physics, with what's actually in our universe?
It's one thing for mathematicians to show that you can write down some sort of weird geometrical system. It's another thing to say that that weird geometry is actually part of the physical world, right? It's a totally different bar to proving that. And I don't think many physicists in the 19th century thought it was likely that non-Euclidean geometry was built into the space of our universe. But that all changed with Einstein. So Einstein finishes his special theory of relativity in 1905 and starts working towards building a more general theory, a theory that could include acceleration, which a special theory doesn't know how to do, and a theory that includes the phenomena we call gravity. So in old Newtonian physics, in a Euclidean space, imagine that objects just move along straight lines unless forces act on them. So according to Newton, an object like a planet or something in its orbit moves along ellipses because the force of gravity causes them to depart from the straight lines that they were following. Einstein had this different idea. He said, well, gravity is not really a force. There really isn't deep down a force of gravity. What happens is when you put matter or other forms of energy in space, it changes the geometry of that space so that that straight line, if you will, looks curved. So the Earth in Einstein's imagination or in his depiction follows the elliptical orbit it follows, not because a force is acting on it. There isn't any force of gravity in his system, but instead because that is where the geometry of space tells the planet to go.
So So Einstein's theory of general relativity completely changed how we think about gravity. It's not a force, there's no action at a distance at play. It's just space itself being curved and deformed in the presence of mass. And this effect is captured by the central equation of the theory, what we call the relativistic field equation.
This is a simple looking equation that's really hard to work with. My guess is, most physics students never really manipulate this equation well until grad school, and only then if you take a class on, cosmology or maybe specifically on general relativity. What it really does is it relates the distribution of energy and matter in space to the geometry of that space, or space-time, if I want to be more precise. So the geometry is uniquely determined by the energy and matter that's present, and vice versa. They're kind of directly coupled to one another. Now, in practice, it's really hard to manipulate this equation. It's a whole bunch of these things called tensors, and it's a bunch of nonlinear behavior. There's a reason why you don't learn about it in intro physics classes, but the idea is fairly simple and profound. That this idea that if you know where the matter and energy is, you can work out what the geometry of that surrounding space must be. The reason why physicists treat general relativity as truth in a certain sense today, at least provisional truth, isn't that we think Einstein's so smart or that it's so theoretically attractive or anything like this. It's really just because it works. So there are a huge array of observational facts that give us confidence that general relativity is a good description of nature. At the time, Einstein knew that Mercury's orbit didn't match the predictions of Newtonian physics precisely. Like other planets, it follows an ellipse, and that ellipse, the orientation of that ellipse kind of changes from year to year. We call it the precession of the perihelion of Mercury's orbit. And it was about 0.01 degrees off per century, I should say. It precessed at a rate 0.01 degrees per century different than Newton would have predicted. People had various ideas about how to solve this. They hypothesized a new planet called Vulcan. That's where Gene Roddenberry got the name. And astronomers looked for Vulcan, but they didn't see it. Einstein showed us that, in fact, if you account for gravity using general relativity instead of Newtonian gravity, you can explain why Mercury moves through space in the way it does. Also, there was this famous solar eclipse in 1917, and that provided astronomers with an opportunity to measure light being bent by the sun's gravity as it passed by the sun. And that, again, agreed with general relativity, or the predictions it made. And then really in the second half of the 20th century, we started doing really a variety of high precision tests of general relativity. This is like things like bouncing lasers off the moon and sending probes through the solar system, and even doing things in like recent years, like watching the gravitational waves from mergers of black holes. All of this stuff tells us over and over and over again that general relativity is just right, or at least it's right at the level that we can measure it.
For example, and you might have heard this before, without general relativity, forget about having an accurate GPS or Google Maps.
If you didn't account for the effects of general relativity in trying to use the information that their network of GPS satellites collects, it just wouldn't work at all. It would give you wildly wrong locations on the Earth's surface. Anything that's that precise has to take into account the effects of gravity at different locations, and the curvature of space and time around the Earth's gravity.
Yeah, I guess we take for granted how precise GPS really has to be. Like, it can really tell you like exactly where on your block you are. But like at the same time, like we can go to the moon without general relativity, right?
Yeah, I mean, I'm not sure, but I think the whole Apollo program was pretty safe using Newtonian physics.
I fact checked that, and it's true. Your phone uses more modern physics than the Apollo missions did to get to the moon. But let's go back to Einstein, and let's jump to the year 1917.
And in 1917, Einstein decides to apply the same equations to a more bold endeavor. He's going to apply it to the entirety of the universe. Now, as far as I know, like, this is not something physicists go around doing very often. When people wrote down the equations of electricity and magnetism, they didn't wonder about the current of the whole universe, or when, et cetera, et cetera, et cetera. Like, I think it really speaks to Einstein and the grandiosity of his thinking that this would be one of the first things he would try to do. So like I said before, these equations are really hard to manipulate. So he had to make some simplifying assumptions. In particular, he assumed that most of the energy in the universe is made up of matter, and that matter is distributed in a homogeneous and isotropic way throughout the universe, basically assuming there's the same amount on average matter everywhere. So this isn't a perfect assumption, of course. There are stars and planets and things that are big clumps of matter, and then there are other places that are big voids. But on cosmological scales, it turns out to be a pretty good assumption. If you take some billion light year cube or something and ask how much matter there is in that and compare it to some other billion light year size cube, you'll find it's about the same. So it turns out that modern astronomers and cosmologists would confirm that Einstein's assumption was a pretty solid one. But in a sense, Einstein got lucky in that respect. So from those assumptions, you could take the gravitational field equations and derive from them something we call the Friedmann equations. And those describe for a amount of matter, a certain density in the universe, how the universe's geometry should be, and how it should evolve, how space should change with time. If you just look at these equations for the first time and you don't have any prejudices or any ideas, any preconceived notions about what the right answer should look like, you very quickly learn that space should change. It should expand or contract. But Einstein hated that idea. For some reason, I still don't really understand what it is. But when Einstein looked at this conclusion, he said, no. Like, he wants the universe to be eternal. He just thinks it's common sense that the universe isn't changing. And plus, in his defense, if, you asked astronomers, is there any evidence that the universe is changing? They'd say, no, it seems to be the same as it's always been.
Yeah, I wonder if it's like, if it wasn't even like a physical intuition thing, but almost a thing that like stressed him out. I've talked to people who like have real existential anxiety about the idea that there was like a beginning or that there will be an end to the universe. So it could have just been like that kind of anxiety for him.
Yeah, I mean, there are all sorts of examples of people like feeling overwhelmed with sense of dread or whatever about the universe ending one day. No matter how many billions, trillions, or quadrillions of years from now you're talking about, it doesn't seem to matter. The idea that time would be finite is upsetting to some people, I guess.
Right. Yeah, it's funny. I've never felt that kind of deep existential dread about it.
I also frankly, I'm way more relaxed at the idea of a finite timeline. It's something that goes on forever. That's much more upsetting to me. I'm much more comfortable with a universe bounded in time. But Einstein seems not to have been. He just couldn't wrap his head around that. It couldn't accept that very easily. At least not at this stage in time. So he goes back to his field equations and adds a whole new piece to them to avoid this conclusion that the universe should be changing. This piece we call the cosmological term. Sometimes people call it's the cosmological constant. Technically, the cosmological term is a term in the equations that's proportional to the cosmological constant. And what this term corresponds to is he's basically postulating that a given volume of space, any given volume of space, any point in time or any point in space will have a certain amount of energy inherently built into it. So if I take a cubic meter of space and I take all the atoms out, I take all the photons out, I totally empty it as much as I can, there'll still be a certain amount of energy in that. That's what the cosmological constant or cosmological term does. And when you include this, if you set it to a very precise value, Einstein showed that you can find a static solution. The static solution got to be known by other physicists around the time as Einstein's world. And I kind of think they might have been making fun of Einstein a little bit with this, but I'm not sure.
Sounds like it.
So let me describe the solution that Einstein came up with. So first of all, it's not expanding or contracting. It's just the size and shape of the universe stays the same indefinitely into the future and past. The space is uniformly positively curved. So if I take any 3 points in space and draw straight lines between them, that triangle will have angles that add up to more than 180 degrees.
Right, or in other words, like the universe is like a giant sphere.
Yes, it's a three-dimensional sphere, whereas a normal sphere is a two-dimensional surface. This is a three-dimensional analogy to that, analog to that. Also, like if you follow, just like on the surface of the sphere, if you follow parallel lines, they converge, just like two parallel lines at the equator meet at the North Pole, that sort of thing. So yeah, it's definitely a non-Euclidean geometry that's built into Einstein's world. Also, just like the surface of a sphere has a finite area, Einstein's world had a finite volume. But it doesn't have any boundaries. It's not like it ends somewhere. It's just that if you go far enough in one direction, you'll eventually come out the other side of the universe. It kind of wraps around on itself in all directions. Just like if I walk west far enough, I will come out the east side of the globe. Same idea, but in 3 dimensions again. Turns out that it's about a 10 to the 22 mile trip around Einstein's world, so don't expect to get there anytime soon. And Einstein published this. This was the first real paper in cosmology in the history of physics, as far as I'm concerned. But there was a pretty big problem with it. So shortly after, Alexander Friedman, a Russian physicist, named the Friedman equations are named after him, showed that Einstein's world just wasn't a stable configuration. Now, remember before I said that one of the assumptions Einstein made was that the universe was homogeneous. So there's the same amount of stuff everywhere. If that assumption is even slightly untrue, Einstein's world will begin to fall apart. The places that are a little more dense than others will start to contract, and the places that are less dense than others will start to expand. And if you wait a long enough amount of time, you don't have anything like a stable configuration at all. You have expanding patches of space and contracting regions of space. And it just brings us back to this, big overarching conclusion that if you take Einstein's theory seriously, and we have every reason to, then space has to change. The size, shape, geometry, whatever of space has to evolve as time progresses. Just a few years later, Edwin Hubble and Milton Humason actually observed for the first time that our universe is expanding. I personally consider that to be one of the, if maybe not even one, maybe the most important discovery in astronomical history. And it's what we're going to talk about next week on Why This Universe.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.